if you just keep a few good tips, then you can understand the material quite well. Okay. Well, what we talk about is just the interference, and everybody understands what constructive interference and destructive interference is. You can write constructive interference is that you see all the energy is concentrated at one point in space or in time. And for destructive interference, basically you'll get a dark fringe. So suppose you have one piece of the atheron, okay? Suppose I'm holding one piece of atheron, perhaps from my box, if I'm holding one piece of atheron, and then you send light on this piece of atheron. If you have a destructive interference, what would you see? If you have a destructive interference inside this piece of atheron, how would you expect? It means the energy cannot go through. So easy, right? It means the energy cannot go through if you have a destructive interference in this piece of atheron, inside this piece of atheron, not outside, okay, inside this. If you have a destructive interference, this means that you get reflection. Okay, you get reflection. You see something in your eye because the energy reflected back. And then you can tell me if you have constructive interference inside this atheron. What do they mean? Hey, this guy is going to take a lot of energy, right? Because you have constructive interference inside, and then the energy can be built up. Where is the energy from? From your input. So you get no reflection from this piece of elements if you have constructive interference inside this. Well, when you think about the physics, you want to think about the whole thing from this guy's point of view, not from your point of view, from this guy's point of view. So again, if you have a constructive interference inside these elements, this means it's going to take a lot of energy from you, and then you don't get reflection. And this is exactly what we are talking about right now. When you have, this is a reflection spectrum. When you have resonance inside the atheron, then you get nothing reflected back because you take all the energy from you. So then you have 100% visibility for this reflection spectrum. Now think about this. When you see total darkness, from the sky, this means that the energy does not go back to you, right? Because this guy is happily absorb all the energy from you. Can you see this cartoon? 脑袋里头可以有一个卡通的影像嘛 right? This guy is happily take the energy from you. All you will see is this total darkness. Alright, so this is the very simple tip when you try to understand those plots. And then the transmission spectrum is just complementary to this. It's just complementary to this. So when you add these two together, you get your energy conservation. So this is 1 minus this. Okay. So the discussion of this just complementary to this. Okay. When you have off resonance, inside, the energy will go back. So you see a bright fringe reaching your eyes. When you have the resonance inside the atheron, then the energy just goes through, and then you have a peak right here. So they are complementary to each other. And turn out that the coefficient of finesse determine the width of this spectrum. Well, what do we mean by coefficient of finesse? This means that how good I can store the energy into this. How good I can store the energy into this, inside this. This is the physical meaning of the coefficient of finesse. If this guy is big, this means that, hey, I can store a lot of energy inside. Okay. If I am able to go inside this, I'm going to feel a big electric field if this F is big. Okay, so to establish to store a lot of energy inside, well, the door is quite narrow. Okay, because the constructive interference, the condition become very stringent. If you want to add a lot of, for example, if I want to add a lot of effort together from a large group of people, the effort is going to be much more stringent because everybody needs to do the same thing at the same time. Okay, so the requirement becomes stringent. Okay, so can you create such a cartoon, a physical picture in your brain? All right, so then let's try to quantitatively calculate the width of this. Okay, so guys, you got a point, right? On resonance, you're going to have a very narrow bandwidth because the constructive interference, the requirement from a lot of waves become very stringent. All the phase has to be aligned for the wave inside. So you only have a narrow window to build up this constructive interference inside these elements. When I say narrow window, this means that well, you need to align all the frequency wavelengths very, very well within this spectral width. All right, so let's try to understand the width. Well, the width of this array pattern tells you the bandwidth to store energy into these elements. Okay. Previously, we plot this as a function of the phase, the optical phase difference, right? And when the optical phase difference is integer multiple 2 pi, then you have a peak, you're on resonance. But there's a certain width associated with it. And the array function governs this pattern. So let's pick the array function and try to discuss the width. Well, if something goes back to 0, then it's easy to tell the width, well, from here to here. But in fact, this width definition is more useful, right? This width definition is more useful. So let's try to cut this into half at the half amplitude and determine this width. Okay. Well, when you determine the width of something, how do you determine the width of something? Well, how wide am I coming into here and then measure the distance from here to here, right? Because this is a hard boundary. But if I were something that extends in this direction, how do you determine the width? Well, measure the width at the half amplitude. Take my height and then cut me at the half amplitude, and then you get the width. All right, this makes the addition almost smaller, right? If I have, if I were something that is extended to infinite, the width, in fact, is not infinite, right? So measure my height and cut myself into the half height, and then measure the width. So this is the way to determine the width of something if you see extended the amplitude over some space. You should agree? So this makes sense to you. All right, let's measure the total height and make it 1 and cut it at 0.5. Then you get a width, right? So you set this to be 1/2. You set this to be 1/2 and measure this this value, okay? And assume that this is starting from 0. So you set it here. So this value, in fact, is just the half width. And then you multiply it by a factor 2 to get the how we call full width at half maximum. So now you understand this FWHM, full width at half maximum. 它的一半高度的地方。All right, so you get this. Hey, so this is consistent with what we just discussed. If you have a large coefficient for this, you can store energy into the system, but the constructive interference condition become more stringent. All right, so when this F is big, this width become quite narrow. All right, so this is the good description about the width of the area function. All right, so specifically we can write down this gamma full width have maxima as a function of the reflectance. If you just pick up the definition for this coefficient of fineness, and then you get this. Okay, so the question is, well, if you want to have a good, very narrow width, what does it mean? It means the selectivity is very good. If you use a piece of ethylene, in a moment, I lost it. I don't know where it is now, so I put it back. Interesting. Okay, so if I have a piece of ethylene like this, and then I want to use it as the instrument to select something, right? If this is very broad, then perhaps it's just a piece of filter. It's not an instrument to measure the wavelength. For example, this is function data. Data is a function of wavelength. For example, if I want to use this to measure the wavelength, okay. And then I want to allow this certain wavelengths to pass, and then reflect all other wavelengths, just like the filter you are doing with LXD, right? So this means that if I have a narrow bandwidth, this means that the selectivity of this ethylene is very good. So I can use it as an instrument. All right. So you want to narrow down this for certain application. What would you do? Hey, you increase this R, you reduce this width. So you want to have HR coating here, HR coating here. So you just go and tell the LSC, hey, I want to do this coating. Then it's going to be a good ethylene. High refreshing coating here to increase this R to approach 1. Then this becomes very narrow. So this is how the student, the engineer, LSC in our group are working together with each end for certain optical coating. All right, so each end, you have the first-hand experience now on optical coating, right? If you want to build an ethylene, hey, increase this R. Then you narrow down this, then you have selectivity for your instruments. Okay, each of them got a point, right? So this is very practical. What we are learning here is not just the formulas, calculations, but in fact, this is a set of tools for you to do applications. A set of tools for you to do applications. All right. Now, let's go a little bit further. Now we talk about wavelength frequency, not just the abstract, some terms that give you the some abstract thinking. Finesse, constructive interference, destructive interference are some sort of concept. But now let's get down to applications. When you talk about applications, you talk about wavelengths, right? You talk about frequency. All right. So let's replot this data as a function of frequency. Well, remember this data, this phase is a function of frequency. 1 over lambda is a frequency. 1 over lambda times C will be the frequency, right? So whenever I talk about 1 over lambda, I'm talking about frequency. And this is called wave number. This is called wave number. Okay. And when we talk about wave number, it's the same as frequency. If I just multiply this with speed of light. So you need to get used to this term, 1 over lambda. Especially in chemistry, people use this 1 over lambda to talk about frequency of the wave. Okay, Shuka, can you take it? Okay, you're from the 医管系, am I right?
那个原科院学士班。
Oh, 原科院学士班, okay. So more people, in fact, in your college, talk about this wonderful number. Okay, people in chemistry and a lot of people in physics talk about this instead of this mu as a frequency. Okay, so we can plot this as a function of frequency 1 over lambda. Okay, and we can also plot this as a function of reference, of course. So then, if we plot this as a function of frequency, then we start to think about the resonance corresponding to some frequency, the resonance corresponding to some frequency. So think about that. Hey, I have one piece of epsilon, and then I send laser along this direction, and then I start to tune the frequency of this laser or tune the wavelength of this laser, and at a certain frequency, I don't see transmission. At a certain frequency, I see good transmission. So I'm scanning along this line. Occasionally, I don't get transmission. Occasionally, I get very high transmission. Then, I don't get transmission, and then later I get very good transmission. Now, I'll be interested in knowing how far I need to tune the frequency of my laser so that I get something going through this again. Well, initially I get a peak transmission, and then I start to tune the frequency of this guy, and after some time I get a high transmission again. And this range is called free spectral range. And according to this plot, this means that the delta will go through one integer, will go through a range of 2 pi. Right? So let me just to simplify this calculation, let me do a normal instance. Okay, so I set theta t to be equal to 1, and then I start to scan the frequency of reference 1 over lambda 1 or 1 over lambda 2, and set it equal to 2 pi, and start to calculate the separation of these two reference or separation of these two frequency. And then I will be able to calculate the free spectral range. Okay. Any question about this? No? Quite straightforward, right? I'm scanning the wavelength. Equivalently, I'm scanning the frequency to get a 2 pi phase shift. And then I determine the frequency range. That is the frequency, the free spectral range. Okay. So if you finish this calculation, the data lambda free spectral range or data mu free spectral range, then you end up having a compact formula. And this is something that you want to remember forever if you're working in optics. The free spectral range of a resonator is given by speed of light divided by 2 times the thickness, and then divided by the refracting index of the material. Okay. So this is the free spectral range that you'll be using all the time if you will be using a resonant element, C over 2D. Okay, C over 2D. And C is the speed of light inside the material. C and F is the speed of light inside the material. Okay, so basically it's the speed of light divided by 2 times the thickness of the atom. All right, is there any question? Okay, now the finesse of an interferometer defines as this. Now, we previously have coefficient of finesse, right? The reason we have coefficient of finesse, remember, that is to simplify this expression. We define the coefficient of finesse right here. That is to simplify the expression, but there's no physical meaning associated with it. Okay, and there's no direct, obvious physical meaning associated with it. Of course, we say that if the coefficient of finesse is big, then the width can be small, but that is not direct physical meaning. the main purpose of this F definition is to simplify this transmittance expression, and we call this area function. But now, let's define something that is more physically transparent. To have a more physical meaning, that is the free spectral range, the width of this. Free spectral range divided by the width of this. So think about, you have a width of this, and then you have a width of this. Then we'll be interested in knowing the ratio of this width to this width. Well, regardless of any kind of formulas you'll be seeing right now, just think about, well, if you have a big width like this, and you have a small width this, and then you'll be interested in knowing the ratio of these two, right? Okay, just like if you live in the room, the total width of this room is this big, and my width is this big, I will be interested in knowing the ratio of this, the width of the room to me. And then I will say, hey, I have a big space to live, or I have a small space to live. This are all you raise in a problem outside or in the dormitory. In the dormitory, right? You have to have a big room, but the dormitory is too small for you, perhaps. Okay. How do you describe big and small? That is really relative to your size, right? So you want to rent a room that the room size is a big ratio to yourself. Then we say, hey, this is a big room. All right. So this is a useful information when you design some instrument. And then we take this ratio to be a term called finesse. That's it. So next time when you see this finesse, the term, it means that, hey, that's the ratio of the big room to me, to my size. So of course that a big finesse is going to be advantageous. So when you make a comparison, in fact, it's easier for you to remember things for a long time. Okay. All right. So the whole range is 2 pi. The whole range is 2 pi. The width of this is the already calculated. That is gamma value. Okay. And this is the definition in the domain of delta. Previously, you calculate the width of this. When you plot this as a function of the phase, delta. So this point to this point, the separation 2 pi, divided by the width give you this. But you can do the same thing. You can do the same thing by plotting the function frequency or wavelength, right? So equivalently, this finesse is also the width in frequency domain to the separation of the free spectral range right here. The same thing. So I can label this as nu or lambda. Okay, this something that I put it on for you on the slides. All right. So this is the definition of finesse, and this finesse is more useful because now the definition of finesse has a very clear physical meaning. Okay, the coefficient, again, the definition of the coefficient of finesse right here, it's just to simplify this expression to make it nice looking. But sometimes you understand that the nice looking is not useful, especially sometimes to people. Yeah, so nice looking is good, but not so useful. Okay, sometimes. But now, if you have a good physical meaning to define a term, then it becomes a useful definition. All right. So I try to sort of talk about optics in terms of the practical experience you have in your life. I hope that it will be easier for you. All right, free spectral range. Now, when people start to use this piezoelectron to do instrumentation, then people consider more. For example, the resolving power given the wavelengths. So the scenario is like this: I have a laser going through this electron, and then I see a narrow window for resolving this wavelength, right? And then next time I could be using this. Now it's a green laser. Then again there's a narrow window associated with it for this wavelength to go through. So the wavelength versus the width becomes something that tell you the resolution. For this experiment, the resolution will be different from the resolution of this experiment. Okay, because the door, the opening door is different. For example, that for somebody that has a big size, want to go through this door, and for somebody very slim to go through this door, the situation will be different. Okay, and so this resolving power tells you, given a wavelength, how big the door is for you to open and allow the energy to go through. So this wavelength versus the width. Now it's not the size of the room versus the door. Okay, this the definition for the furnace. For this definition, think about this. This is the size of the room versus the opening of the door, for example. Okay, but now for this resolving power, is that that is the size of you versus the opening of the door. Can you imagine that? Okay, let me say again. The definition of the furnace is the ratio of this range to this range. That is more size, the size of the room versus the entrance door. Right, you open a door like this for the energy to go through, and this is the whole size of the room. But then, this resolving power is more like a fat guy want to go through a small opening door. Okay, or a slim guy want to go through an opening door. Okay, and the guy coming in is a laser, just like a laser. So this is resolving power, and then the definition of this furnace is the whole range divided by the opening, the bandwidth. And you can connect this to this. If you connect this to this, then you end up having this expression. Furnace multiplied with this QND over wavelength. So in fact, that's the physical meaning of this. If you do a little bit organization, you find that hey, this is in fact the ratio of the ratio of the half wavelength between these two boundaries. Okay, between for given set of the boundaries. Well, you can have half wavelengths inside. You can have, for the fundamental mole, you can have the second higher order mole, and then you can have more lobes inside these two boundaries. How many half? Well, the width of this is half wavelength. Given an electron, you can count the number of half wavelengths inside. We call this N. The thickness of the electron divided by the half wavelengths inside the material. Shukai. You got it, right? So this is N. Hey, so resolving power, in fact, is a number of half wavelengths inside this multiplied with furnace. It becomes very simple formula. Okay, so if you want to have a good resolving power, if you want to have the well, if a fat guy want to go into this room, go into this door, if I'm very, think about if you have a fat guy want to come into this door, in fact, can be used to measure how fat it is. Well, we just make a comparison. Well, this door is, the fat guy is about 3 times this door. And we can tell the people that, hey, this fat guy is 3 times the width of this door. So this is resolving power. You smile, so you understand that Shukai clearly catch the point, right? All right, and then this resolving power is very simple, given by this expression. And then again, finesse. What is finesse? Finesse is coming, is this door, the size of this door, compared to the width of the whole room. Okay, so this is the sort of analogy that I want to draw for you. All right, so finesse is therefore an important figure of merit for describing the spectral resolution of an interferometer. So this is the important concept and have a good physical meaning. And again, the coefficient of finesse is just a term, a factor for you to simplify the calculation for the area function. Okay, make it pretty. And again, I told you that sometimes good looking does not mean that it is always useful. All right, and the question about this. In fact, this class can be very relaxed because we don't have many people, and I like to have a small class because we'll have more chance to discuss. All right. Each-end, do you have any thinking so far? So far, so good. Yeah, good. All right. But when I get senior, then I really like to have a small class because we can have a lot of discussion and it's more relaxing. All right. Suka, fine. All right. So let's move to the next topic. We'll be going to. Okay, I want to move to chapter 4 now. And for chapter 4, the first part of it, if I divide into 2 parts, the first part of it is the more or less straightforward and intuitive. But the second part is more elaborating in calculations. And I know that the engineering students sometimes do not like a lot of calculations. But let's try to catch the key point and try to understand it, okay? For this part, for the first part is quite intuitive, so let's take a look. Well, we'll be talking about diffraction. And since high school, you learn that if I have some obstacle, if I have some slits, just allow the wave to go through this small narrow channel. You see something that is unusual. Okay, you see something that is unusual. And in fact, I used to do this experiment for a long time, but I'm not sure I can do it. All right, I have a slit in between my finger, and then I send the laser through. If without the slit, you're going to see this. With the slit, see how you will see, in fact, you see nothing because the laser does not quite go through my finger well. Ooh, you see something? Hey, this is real. This is real. You see diffraction of the laser. Ooh, you see multiple lobes. So my finger is good. Aha. Give me a smile. Okay, we just see the slit diffraction. Right? We can reduce it. Yes. You don't quite see just a spot. You see the diffraction lobes. See diffraction lobes. Amazing. You see this. So something happened if I have a boundary, okay? And what we are seeing, in fact, is something like this. It's far away, far away, much larger than the wavelength of this laser. And we call this the Fraunhofer diffraction. Okay. But in the near field, if you just try to take the diffraction pattern very close to the slits, you see something more. You see something that has more structure. Okay, and so this is a near field diffraction. We call this kinetic diffraction. Far field diffraction, we talk about Fraunhofer diffraction. When we say far field diffraction and near field diffraction, it's a comparison with the wavelength. If you get closer to the boundary within a few wavelengths, then you start to see this. In the far field, you see this. And we're going to talk about this because this is going to be much more easier in terms of calculation. All right. So this is the starting point for the diffraction. All right. So the first part is going to be associated with the Fraunhofer diffraction. Well, when we talk about something that is much larger than the wavelength, this means that it's going to be a plane wave approximation. Okay, when you have a wave going over a long distance, then the wavefront is more or less a plane wave. Shukai, do you agree? If you have a spherical wave going out like this part of the wavefront is more or less a plane wave. Going up. Yeah. So think about you have a plane wave after a long distance propagation right here, and then on this, every point gives more or less the same amplitude, just to simplify the calculation. And then if we talk about interference, then you want to understand the optic path difference between this ray and this ray and this ray and this ray. You see that the optical path difference can be calculated. If we just treat this as a straight line, and then this is at the far zone, you have interference from those plane waves. Does it make sense to you? Hurry, right? If you have the discrete sources like this, and then you need to care about the optical path difference. For this one, you have d sine theta. Theta is this small angle right here. This is d, is the separation of these two sources. And between these two sources, the separation between this line and this line is going to be this section. Will be 2 times this section. So geometrically, you can feel it, right? This is twice as big as this. This is 3 times as big as this. This is 4 times as big of this. Right? So each for adjacent lines, the optic path difference is this big, d sine theta. Okay, whatever it is, let's just sum over all the field in the far zone. Sum over all the field in the far zone. This term is R1 distance. This term is R2 distance. And then for this term, you have Rn distance. Just add them together. Okay. And then you take out, for example, take out the exponential I k R1 to get this. So you'll be counting the the path difference relevant to this path. You'll be counting, you'll be measuring this length versus this, measuring the length versus this, and you see that the path difference is 1 difference, 2 differences, 3 differences, 4 differences. Okay, so you can sum this together because you knew this phase difference will be integer multiple of b sine theta. Okay, the adjacent one will be the b sine theta. And if this is n minus 1, then you have n minus 1 here. So you have a constant, you have a sort of constant phase difference between the adjacent field. So you can do a summation, right? You know how to do this summation. One plus, for example, A plus E, 2A plus E, 3A, that exponential n minus 1, A. You have 1 minus E, A, 1 minus E, A. Kind of integration. Everybody has gone through this. Shukai, you do this for sure. Right? Are you familiar with this? Yes. Right. And I'm sure you know about this, right? So just pick up this formula and do the calculation. And what we care is the intensity. So let's do an intensity calculation for the final form. All right, let's do an intensity calculation to get this simple result. Don't forget, this delta is the optical phase difference between the adjacent rays. So you have this intensity like this. Right, let's take a look. Because this n could be big, so you oscillate very fast. Agree? If this n is really big, then you oscillate like crazy. And at the bottom, you don't have n, so it varies slowly. Which one can you get it, right? So you have a fast oscillation divided by the slow oscillation. And if this is really slow, this does not change this too much, except that if this is zero, if this peak, if you have a large value divided by 0, wow, then it could be something. When you have something divided by 0, well, we need to figure out the value, and you knew it. You knew it when you have something divided by 0, and this something could be 0, could be something, then you need to apply this L'Hospital's rule to get the value. So when you have this 0 divided by this 0, you apply this rule, and you find that, hey, this is big. N squared I 0. Okay. So it turns out that if you divide this with this, you get this huge enhancement at a certain value of delta, which is the resonance condition. Okay. For constructed interference, principal maxima will happen when this becomes 0. Right? Usually you know that something divided by 0, it could give you a big number. Right? So how do you get this to be equal to 0? Well, if this is an integer multiple of pi, then this number can be really big, or this delta to be equal to integer multiple 2 pi for constructed interference. It is big. Okay. And how big it is? you gain a factor of n squared. What is n? N is the number of sources, 1, 2, 3, 4, 5, 6, 7, and so on. So if I plot this n equal to 5, you get an enhancement of 25. But this is wonderful because when human beings looking into some physical parameter and get a square dependence, that is nonlinear. And people will figure out applications right away. All right, and while previously we treated this as a constant. There's no variation along this direction, and so we end up having these results. But in fact, sometimes if you have some variation on the source, you could have some modulation on the overall pattern, and that is something we'll be talking about. Okay, so forget about this first. Okay, forget about this first, but be careful next time. We'll allow variation here, and then you will end up having this kind of envelope, But let's wait until we have a chance. Wait until we talk about the greeting formula. So this is sort of the first illustration about Fraunhofer diffraction. And in fact, this calculation is the same as a calculation for antenna. Li Xiaorong, you took my antenna class, right? In fact, this is antenna array. This is the antenna array. And what you get, if you still remember, in fact, this is called array factor. You remember that there's an element factor. At this moment, the element factor is just a constant. And then you have array factor right here. If you have an antenna array, that is the element factor multiplied with the array factor. Array factor comes from fields. Okay, now we have array factor. But for the element factor, single antenna, just a constant value. So this calculation is the same as the antenna calculation we did in the electromagnetic wave. And you share you're my teacher assistant, right? So if you go back to the review the lecture note, you know this calculation. All right, so let's take a 10 minutes break, and then we'll continue. Oh, by the way, we're going to have the second midterm exam. I think it's Monday. We postponed it. We postponed it because the.
It's on 18th May.
I'm sorry.
It is on 18th of May.
Yeah, it's the Monday, the May 18th. The reason is that I have a request from Ioannis, and it turned out that the Ioannis and Stavroura, they perhaps do not pay too much attention to this class. And so anyway, whenever you have a request, I try to accommodate. So if I'm serious, I'm hoping the student can also be serious. Okay. So previously we have the midterm exam here, Wednesday on May 13th. But Ioannis sent me an email, told me that he cannot come to take the exam, so I'm moving to 18. So I hope that you can accommodate this schedule and do this schedule. All right, we'll come back in 10 minutes.